we've got a story about Captain Kittinger, who was the person to have jumped from the highest altitude, and we are asked to show that his record-breaking speed of 275 meters per second, whilst free falling from 3,900 meters, you've got an acceleration here of 9,72. So you have to prove this particular velocity over here with the information that you've been given. Remember that he has free fallen, so his initial velocity is going to be equal to 0. You've been given an acceleration of 9,72 meters per second squared, and you have got a distance of 3,900 meters. You're interested in a final velocity, and therefore you are going to use the equation of motion v squared is equal to u squared plus 2as. If I substitute in my values, I get 0 plus 2 times 9,72 and 3,900. And I then land up with 275,35 meters per second, which is approximately equal to what they gave me, which was 275 meters per second. And I need to convert that value into kilometers per hour. Remember the method. I go 275 meters per 1 second is equivalent to 0,275 kilometers divided by 1/3,600th of a second. Now, if I've got 1/3,600th of a second in the denominator, a fraction in the denominator, you can just multiply into the numerator. So on your calculator, you're going to go 0.275 times by 3,600, and you land up with an answer of 990 kilometers per hour. Of course, if that were the story, there's absolutely no air friction. Also, they gave you a acceleration value over here, which was true when he was high in the sky at 3,900 meters. But actually, as he tends towards Earth, that gravitational acceleration is going to get greater. It goes closer and closer to the 9,8 that we are used to. So you need to just be aware that this is an oversimplification of this particular scenario, but it is acceptable in terms of the information they have given you. Then it says calculate the time taken for him to reach that particular speed. And we're going to keep it simple now. We're going to not add in the 3,5. If you did, it wasn't wrong, but if we're going to just try and keep things simple, we have got a final velocity. We've got an initial velocity. We've also got acceleration. We've also got distance. We've got so many pieces of information that we could use probably any equation of motion. But the simplest one I find to use is v is equal to u plus at. And I go 275 is equal to 0 plus an acceleration of 9,72. And the time turns out to be equal to 28,29 seconds. The next thing is skydivers jump from altitudes that are generally lower, and there is significant air resistance at lower altitudes. So now they're going to start asking me to consider air resistance. If I take a look back at Kittinger's jump, the whole thing took place at very high altitudes. I mean, obviously, eventually he had to have a parachute fall. So there was less air resistance. But now I'm asked to put a dot on my page and to consider from that dot that I have got a downward force of weight, and I have got, and sometimes it's nicer to call the weight the gravitational force, or force due to gravity. you cannot just write capital W. You cannot just write F subscript G. Those are not acceptable when you are asked to draw one of these free body diagrams. The other thing with a free body diagram is that you need to draw it very neatly. You need to use a ruler. And when you are now adding the second line, I've run a bit out of space, but those two lines, if you're going to have them be the same magnitude of force, you need to have them exactly equal to each other. And that's where one of the marks will have come from. Air resistance is the second force. And so what was my question? Draw a labeled free body diagram to represent the forces acting on the skydiver when he's falling downward at terminal velocity. At terminal velocity, remember, means that there is no acceleration. If there's no acceleration, then there is also no unbalanced force. And as I said, they ask you with free body diagrams just to use a dot. Then we've got Zara and Patrick. They're part of a skydiving team that performs acrobatics in the air. There are 7 skydivers in the team who jump from the plane and after one another, each falling to reach a terminal velocity before linking up. Zara is first to leave the plane and Patrick is last to leave the plane. Zara has a mass of 64 kilograms and she reaches a terminal velocity of 45 meters per second. And Patrick, with a mass of 90 kilograms, is going to start off 120 meters above Zara, but he reaches a terminal velocity of 60 meters per second. Consider the forces acting on those bodies and explain one possible reason why Zara reached a lower terminal velocity than Patrick. So you are going to come up with a whole lot of things. So she has less mass. Let's take a look at that. If the mass is less, you are going to find that this arrow over here is shorter, which means you would need less air resistance to compensate for that. And since it would happen more quickly, in the end, those two would land up being at a lower number than if you had a bigger mass. The other thing is that she may have, and it was a valid reason, increased her surface area. Now, what's important in this question is that you took the time to explain a reason. Explain. So you need to unpack it. I'm going to go through them again. She's got less mass, therefore there is less weight, therefore less time is required to reach terminal velocity, and the terminal velocity is therefore lower. Or you could have said she increased her surface area, which isn't enough. You then need to say, which means that air resistance would be greater and it would be quicker to reach a terminal velocity, and therefore it would be a lower value of terminal velocity. In each case, you need to actually explain your answer. Then they ask, what is the magnitude and the direction of the velocity of Patrick relative to Zara when they are both falling at terminal velocity? Well, now what have you got? You've got one person falling at 60, another person falling at 45. So in the same way as if a car was driving, let's say, at 45 kilometers per hour, and another car was approaching at 60 kilometers per hour, the relative velocity, the relationship between those two, would be 15. So it's 15 meters per second that Patrick is approaching Zara. How long in seconds will it take Patrick to catch up? So now we've got a time. He's got a constant approaching velocity, and they need to see how long it's going to be. Earlier, they said that it was 120 meters that he left after her. So I've got a distance. Time is equal to displacement divided by velocity. My distance is 120. Remember, that all of these are terminal velocities. And because they are terminal velocities, there are no accelerations. If there is no acceleration, I may simply use the time is displacement divided by velocity, or velocity is displacement divided by time. I can use the simple triangle when I have no acceleration. The approaching velocity is 15, and therefore I land up with 8 seconds. And then it asks me to draw a rough velocity time graph to represent the different stages of a free fall. You don't need values, you just need to have the stages. So the first thing that happens in free fall is best we label our axes, time in seconds, and velocity in meters per second. And I'm then going to say that to start with, there's no velocity. The velocity increases constantly under gravitational acceleration. So that's stage A. And there's a gradual change, really, until they reach terminal velocity, a constant velocity, which is B.